Okay, cool. So that brings us up to today, where we're going to look at how life ends. I didn't make it there last week, so we're going to talk about extinction a little bit, which is depressing, but also gives us some motivation for our next topic, which is where to find a better place, not a better place, but where to find the next home. And so caring about finding a new home really drives the science of astrobiology, which is the search for life out there beyond our own atmosphere. And so today we'll talk about how we do that. How do we look for a suitable habitat for life? And then hopefully if we get to it at the end, I want to talk about how scientists are trying to generate life on Earth de novo in this process called xenobiology, and what they're learning by doing that, and how that can feed back into what we should be looking for out there, because it's not totally clear that life would look exactly, excuse me, that life should look exactly as it does on Earth. There's really two camps, you know. One set of esteemed experts insist that life would look nothing like it does on Earth. It would use none of the substrates, particularly water. And we're going to talk a lot about water, because water is an amazing molecule, and it seems to be at the heart of life in terms of what we need to create the structures that are essential for our own bodies and all organisms. But if water doesn't turn out to be essential for life, if life could, say, use a different solvent like hydrocarbons, then you're going to be looking for a totally different picture. Cool. So going back to our own planet for a minute, let's try to motivate this search for life out there. So this picture, you guys see that all right? Yeah. This is where Mexico is right now. This is the Yucatan Peninsula. This is like a recreation of what the Yucatan looked like just after it was smashed with this giant asteroid, which we believe now killed off the dinos, and set up conditions for the emergence of mammals, which we can all thank for that. And I think that's a really important thing to remember about extinctions, is that they seem really depressing, and there's a huge mass extinction underway right now. But historically, extinctions always have a silver lining, because from the ashes of some terrible event where you lose a lot of these extinctions, we're losing 80, 85, 95% of the species diversity very regularly, every few tens of millions of years. But new things come out of it, and the progress of that is really quite fascinating. Obviously, we are an example of something that was able to emerge from this terrible event. So the rock that's thought to have smashed into the Yucatan was only somewhere in the tens of kilometers wide. It's not that big, really, because there's things that are thousands of times that large that we know smashed into the moon. And so it's highly likely that things as large as that which smashed into the moon smashed into the Earth. If you think about it, the Earth's much bigger than the moon. The moon can maybe gravitationally clean out some of the debris that might hit us, but we've probably been smashed by things that large too in the past. The problem is, as we talked about with our dating regime, if we got hit with something that was as large as 1,000 times this Chicxulub meteor, there would be nothing left on Earth. It would boil the oceans. It would melt all of the surface rocks. There would be nothing left. All of your clocks, your dating clocks, would reset. And so I think I really want you guys to understand, when you hear people throwing out dates for the emergence of this, that, or the other thing, that the only thing we can say is the last time that happened. And so most of our models for the date of the formation of everything on Earth, including our planet itself, in reality, when you dig down, they're really just talking about the last time the place melted. And so it seems highly likely that it probably got melted a few times. And there's different NASA scientists who will argue that, hey, maybe life emerged multiple times before in the deep past, and we just don't know about it. And that's really something to consider. The director of the Goddard Space Institute, Gavin Schmidt, wrote a paper with a couple other really brilliant people about something they call the Silurian hypothesis, which is this idea that, hey, maybe even if highly advanced technical civilization emerged gazillions of years in the past and we just can't see it. There's nothing left. If you think about it, our technologically advanced civilizations only existed for about 300 years. The Industrial Revolution barely cuts into 300 years back. And so all these things we're seeing around us today, they're not going to last that long if we disappear tomorrow. This plastic will last 500 years that these chairs are made out of. The wood will all rot. The metals will corrode in a matter of a few thousand years. The concrete will be taken over by roots. Basically, you'll just end up with a mound, which will eventually turn to dust very quickly, actually. So there's not much evidence that would remain of a technological civilization. And that's what's really difficult, too, about looking out into deep space, because the thought is that perhaps technological civilizations are only there for a blink of an eye. And so we're looking for something that happened very quickly and is gone now. And we'll get into that a bit down the road. So that event there, it was quite massive. It released something like, 5 billion Hiroshima-sized nuclear bombs, excavated this 200-kilometer crater, but this was 1,000th of the size of some of the impacts that we should expect to have happened that we just have no record of, because everything's melted. What else can we say about Chicxulub? I mean, this is the best one. This is the most studied. The tsunami that was generated by this impact reached all the way up into Montana. I mean, it was wild. And they've been able to find little pieces. When an asteroid hits, it releases these. The heat of it sends all this molten vapor into the atmosphere, and it rains down as these beautiful little glass spheroids called techites. And you can find them all the way up there into North America. So this was wild, and of course, created huge fires and acidified the ocean. The chemistry on Earth changed wildly. And again, complete nightmare, but at the same time, these little biological experiments, these little things that had the ability to crawl underground, live in burrows and hide it out. If you think about the way most mammals behave, honestly, the way that we're probably, what keeps us from coming to class in the morning is the reason a lot of these mammals survived, right? We have a tendency to hibernate through winters. We have fur that can keep us warm. We can build up these fatty deposits that animals can hibernate, bears can hibernate, lots of mammals can hibernate. So there's something really fascinating about those terrible conditions that allowed us to be here today. And we'd like to not suffer one of those again, because of course we'd like to be here in the future. So these big collisions happen about every 20 million years, something the size of the Chicxulub crater, which means we're actually overdue for one, which is a bit terrifying. However, we're on it. So we're going to look at some surveys that are going on that are mapping these. And of course, I don't know if you guys have caught the news headlines, but we're actually developing an asteroid deflection system. And I want to talk about that a bit, because it's actually quite promising. Again, just to look at, this is just looking back into the last, say, 500 million years or so. You can see 80%, 76% species diverse death rate, 95% in the Permian. This is 250 million years ago. And going back, and we can't see that far back, right? The the strange thing about our planet when you compare it to like the moon is there's no big craters on our planet. Our surface is constantly being remodeled. This is where the plate tectonics come back in. Yeah.
One of these events causing rapid global cooling and rapid global warming?
Yeah, it has a lot to do with the chemistry. So what's really interesting is that only one of these events can be distinctly. This one is still up for grabs. This is the 65 million year one is the only one we definitely know. Well, definitely is not fair, maybe, but we're quite certain that was due to this impact at the Chicxulub crater, and obviously sending a bunch of debris into the air blocks out the sunlight, causes cooling. Mammals with their fur survive. This is the story. But a lot of times, if you have, say, in some of these other cases, like the volcanic activity where you have methane and CO2 going, and you can increase the greenhouse effect without blocking the inward coming sunlight, which is really interesting. So the greenhouse effect is really as simple as a greenhouse that you might have in your backyard, where you can let in incident light, but the heat that's radiating back can't get out. Yeah. I think we went over that like right at the beginning, but it's cool. The crater was like 200 kilometers wide, but you're talking about the meteor itself? It was quite small. That's what's terrifying. It was maybe between 2 and 10 kilometers wide. And so what I was saying, I think you came in just a minute late, the problem is that the moon has been hit by things way bigger than that, many times. Things 1,000 times as big as that. And so if we got hit by something 1,000 times as big as that, there would be nothing left on Earth to speak of it. All the oceans would be boiled off. The entire surface would be melted. It would just be a complete, utter disaster. There would be nothing. And so what I was saying is it's interesting because we can't really make any definite statements about that. And what you'll find as you go into science, as you get deeper into it, is that we only tend to make statements about things we know for sure happened. Now, the problem with that is that we reify those into definite statements about what happened. And there's a big difference between saying what we know for certain and what we know happened, right? So if you have evidence of an impact crater like the Chicxulub, okay, it's pretty easy to say there was an impact. But if you have no evidence because the Earth was completely melted, then you can't say anything definite. And eventually the books start to think about it like nothing happened at all. So it's really important to remember absence of evidence isn't evidence that it didn't happen. It isn't evidence of absence, right? And that's a troubling feature of the scientific method. It's just important to remember that all of our statements only can feature the evidence that we have gathered. So this is cool. This means there's a lot of mystery that remains in the deep past, and in, especially when we look out at great distances, we can only make statements about what we're seeing, which inevitably is missing a great deal of information. And so it's always important to remember that the stories we come up with are inherently incomplete. It doesn't mean they're wrong. It just means we can't examine things that we don't know about. We can tell interesting stories. They might end up in science fiction. And I think that's a real good reason to maybe pay closer attention to science fiction, actually. I think it's one of the best genres of literature there is, and it's a pretty new genre. For thousands of years, people told stories about mythical beings in order to reflect their own experiences on Earth. Today, we sort of have started to fold in technology into our literature. And you see it in really great movies and really great books, where a lot of the territory that can't be explored by evidence-based science, but still may have a real basis in reality, can be investigated. And we're going to get into that a bit more. So, there's different ideas about most of these extinctions can't be traced to a definite impact event. And people are always toying with what could cause mass extinctions. People are pretty much convinced that the mass extinction that's underway right now is our fault, which I don't think is unfounded. There's almost no fish left in the ocean, which is crazy. It's not clear the cause of that. Certainly, the carbon dioxide in the atmosphere has reached astronomical levels compared to at least the last few millions of years, which acidifies the ocean. The carbon dioxide interacts in a way that makes it difficult for animals to persist in the ocean. We're also fishing the heck out of the oceans. I mean, it's hard to it's hard to describe the scaling of the fishing that we do today. It's like in the past, the oceans were an unending supply of bounty for the fishermen, right? They go out, maybe they cast a net, and they can collect enough fish for their local tribe or their local town for the whole season. I mean, it's just great. People live like this for hundreds of thousands of years. I think there's reason to believe that humans spent most of their time near the water, actually. Most of the time, you guys, we didn't really talk about this, but this is cool. So we usually think of humans as having evolved from apes. This is how it's basically been taught for 100 years, which is totally reasonable. We are primates. And we think about apes, and we're like, okay, the apes swing around in the trees. Okay, we came down out of the trees. We lived on the savannah for a while. But there's an alternative perspective that actually humans were something originally more like water monkeys. And there's a really good 2-part BBC podcast by David Attenborough you can find. I highly recommend it. It's called The Aquatic Ape Theory. And Attenborough interviews a few different people who worked on this in the 70s. And they basically point out that, hey, all of the original sites where we find the very first bones of humanish beings, they're all right near the water, in caves, right near the water. And there's a few other features that are quite interesting, like the fact that we walk around on 2 legs is very strange. But if you think about humans actually starting out in shallow tidal areas, it makes a lot of sense that we'd be on 2 legs because we're sticking our heads out of the water while we're moving about in the water there. There's also abundant food in the water, almost no competitors for that. You can cook shellfish very easily. You just start a fire and throw them on it. There's a few other little really interesting features that support that hypothesis, like humans, when they're born, are covered with this greasy substance that you only find covering other aquatic mammals, like seals. Humans also have the ability to grow these, they study these people right now, like indigenous people who have been diving for shellfish in the oceans. And they'll spend their whole years diving. And what happens, and this happens actually to people who dive right now too, if they do it all the time, they'll grow these little bony protrusions across their in their inner ear, which protects them from the pressure. And so there's all these little lines of evidence that humans have been tightly associated with water for a very long time. And yeah.
Another thing about that, I don't know if it's about the same tribe, but like I was watching a video and it was saying that they could actually hold their breath much longer too, like up to like 15 to 20 minutes or so.
Whoa, that's a long time. Yeah, it's really, I've been getting really into it too. I do a lot of swimming too and diving. And you can hold your breath a lot longer than you think you can. After you get past this like initial phase, like it feels like, oh, I gotta take a breath. But if you punch through that, you can actually go for a really long time and you can train yourself to do it for sure. So yeah, there's just all these interesting lines of evidence that humans actually needed that ocean. And so for millions of years, we were just scooping out the fish that we needed. That was fine. All of a sudden, we have the ability to literally drag these like huge, football field-sized nets across the ocean floor and take everything. The problem is that, you can't just scoop up the fish you want. You scoop up everything. And so there's a lot of collateral damage from the industrial types of fishing we do today, which is quite tragic, And it's popped its head into the news a few times, but I think the oceans are actually one of the greatest, most obvious symptoms that what we're doing here is probably not the best way of going about it. The species loss in the oceans is rivaling some of these extinctions that we've seen in the past. And so, yeah, that's something really to be considered because it's not well regulated. It's very difficult to, it's very easy to defend a border of a country. You just do whatever you do, put up checkpoints and really regulate your laws within it. The oceans are a lot more tricky to regulate because nobody's out there checking. People can fish in these international waters, and that's where a lot of the damage is happening. Again, it's one of those situations where, the idea of a global government sounds really scary on one hand, but it's also not clear how we take care of the whole place if we leave individual nations to regulate their own extraction, because the extraction doesn't just affect that country anymore. It affects everybody. So that's a problem. That's something that people have to solve going forward. So yeah, there's been a number of these gigantic volcanic eruptions. You guys have probably heard of the Yellowstone caldera, perhaps. There's this huge bubble of magma underneath Wyoming that you'll see a headline every few months that's like, this thing is rumbling. It would be really bad. That would be on the order of a Chicxulub type event. If that thing blew, and it seems to have blown a few times, and there's several of those. So in the last few 100 million years, there's been 11 occurrences of these super volcanic eruptions. The sea levels constantly dipping and rising, right, with the glaciations that we talked about. That could be a cause for mass extinctions. Folks have proposed the massive supernovas could have disturbed our climate to the extent that we'd have massive speciation loss. Supernovas are really difficult to track down because they don't persist very long after they happen. You don't have a lot of evidence of them. So we don't know. And then there was a really popular idea in the 80s that was they called this the nemesis hypothesis, to explain the 20 million year cycle of these extinctions that, there was, we never did ever find our partner star, right? Most stars are born with sisters at least, sometimes in multiples, but almost never alone. And so the thought back in the 80s was, okay, well, there's this other star, it's out there. Maybe it's a dark star, maybe it's something like a failed star, like a brown dwarf. And its period is such that it destabilizes the Oort cloud, which sends all sorts of things hurtling into the interior. Again, we don't know because massive impacts are going to be invisible to us. And so maybe. But one thing happened back in the 90s, you guys are probably too young for this, but there was this comet that came into Jupiter's vicinity and ended up impacting it. And it made quite a mess on the surface. Jupiter barely has a surface, but it led to these several impacts. And I think that this really reawakened people's concern about our local environments and how many objects were out there causing a problem. And so people got to work around that time as a result of this. This comet was called Shoemaker-Levy. And I couldn't find a good picture of it. This is an artist's drawing. But they were able to, I think the telescopy wasn't as great as it is now, so the imagery wasn't great. But you see these little flashes as it was impacting, and there were several of them. And so there was a congressional hearing about this at the time, which is quite interesting. The representative asked one of the NASA scientists, he said, "Are we technologically capable of launching something that could intercept an asteroid?" The NASA official says, "No, if we had spacecraft plans on the books already, it would take a year. Typically a small mission takes 4 years from approval to start launch." And so it was essentially established that this lack of a master plan, or even a search mechanism to log all of these potential asteroids was completely absent. And so people got to work on that. And, you know, this has been a real success story in modern times. You know, it's good to point those out when they happen. But there was this mission that was launched called the DART mission that just went down. And it essentially, NASA wanted to, well, a lot of international collaboration went into this. But they found this asteroid that had a little moon on it that was orbiting it. And their goal was to smash into the little moon and see if they could, by doing that, they could change the orbit of that moon. Because, as we know, if you change the orbit, you can deduce essentially how much momentum was transferred to it. And therefore, we could scale up our idea of what we would need to do to avert something actually hitting our planet. This is a really good sign. I was actually really relieved to see this happen because for the previous 20, 30 years since it was pointed out that this was a problem, nothing had been done. And this was actually something of a wild success in a way. So they actually took something that was it was only 600 kilograms, and they smashed it into this rock, this moon, and they were able to divert it in an interesting way. So this is kind of a diagram of how it went. They hit the thing head on. You can see the little moon orbiting this way. The DART probe came and slammed directly into it. They actually flew a little satellite behind it so they could get it was like a selfie stick, basically. And they were able to alter this orbit. And so this was good. It gave them some idea of how much would be necessary. So the Earth's like 13,000 kilometers across. You could avoid getting hit by an asteroid if you just shifted its trajectory by something like half of that. And so the tiny amount, if you just were able to shift some asteroid's trajectory by like 2 centimeters a second, then over 10 years you could basically miss the Earth. So you don't need to hit the asteroid that hard. You just need to A, know where it's going and know that you can alter its trajectory. So we've sort of checked off the box for the second aspect of that. We can get something out there pretty quickly. We can alter its trajectory. The final remaining question is, can we find everything that's dangerous to us? And that actually seems to be going pretty well. Let's see here. So this is the survey of all of our near Earth orbits of these objects that are something like 1 kilometer across. And Congress asked for this map to be made within 10 years, and they pulled it off. But as you can see, that's a lot of objects to keep track of. And this is good. Of course, if we get hit by something smaller than 1 kilometer, that's going to be pretty bad too. So we'll need to continue to expand this range, and that's going to only come with advances in our telescopes. So, there's some hope here. The chances the chances of us getting hit by something, dying by an asteroid impact, have changed by like a factor of 10 just since this collaboration of these two missions, which is really good. So we're able to at least decrease the probability that this will happen, but there's still a lot of work to be done. And I think that folks will keep working on this, especially as we look out and we see impacts happening regularly on other bodies. There's been a few in our lifetime. There's been a few on the moon too, which have been visible that would have been pretty bad for the Earth. So, and then this thing is called the Space Guard Survey, tracking these near-Earth objects, and some other cool stuff has come out of this near-Earth survey. In particular, they discovered the first interstellar object, which is a really, really interesting story. This was Avi Loeb at Harvard, who was a really fascinating dude. And he was digging through the NASA data, and he found this one trajectory that looked like this, which is not how trajectories are supposed to look. As you can see, the thing comes in, it makes a close pass to the sun, and then it goes almost at a right angle away from the sun. And Avi did some searching and realized that not only is this a strange trajectory, but this thing seemed to have come from outside of the solar system, which was the first time that NASA had ever acknowledged that objects even did come from outside of the solar system. And they looked a little bit further into this object, and they found it was quite strange looking, actually. Sort of looked like this, which is very strange. So Avi thinks it's an alien. And he's a really interesting guy to talk to. He came on our podcast, and we sat down and discussed this for a while. And he's since found a couple of these other interstellar objects, including one that crashed into the Pacific Ocean. And he's mounting an expedition out there to try to dredge this thing up from the bottom of the ocean right now. And so they're actually filming a Netflix documentary about this, which will be really cool. Yeah, we'll get to that. Yeah, I'm not familiar with that term. Yeah, that's a real nightmare too. If we hopefully we'll make it to aliens today, but yeah, they're probably not. The aliens we'll encounter may not be the funny green men. They might be the tiny green men, and that would also be a disaster for us, perhaps. Yeah, I mean the little ones are probably more concerning, right? I mean pandemics are real, and that's an issue, and yeah, disease regularly killed off huge portions of the populations in all these towns across the world, quite regularly, every 100 years or so, killing off a quarter of the population. Plagues were quite common before antibiotics, and yeah, so that's a real concern. We'll talk about that too, because there's some ethical issues with the search for extraterrestrial life. Do we really want the aliens to? Do we really want to find the aliens? Do we really want them to find us? Is that a good idea? So yeah, Oumuamua is the name of this asteroid, and it's a very strange one. And they've been continuing to find these interstellar objects, none with quite a strange shape and dynamic. So Avi thinks that it was definitely some sort of an alien drone or something that came in to survey the solar system. Maybe. It seems like if it was, though, that these aliens are friendly because they didn't kill us off. So that's good news. There's been a lot of talk recently about the United States government and NASA revamping this search for UFOs and so forth, which is very strange because you would think that if aliens were actually here and in contact with us, that they'd probably have either killed us off or they were definitely talking with somebody in the upper power structures. So I can't quite piece together what this is all about. But let's back it up a little bit. So this is our motivation for why we should be paying attention to life on other planets. Perhaps it's perhaps we'll need to find a new home, and so if we understand what life needs, then we'll be able to, in other words, if we understand extraterrestrial life, we'll know what to look for better. And then we'll have to eventually find ourselves a new home anyways, because planets don't last forever, unfortunately. Now, this idea that there's life everywhere is a really old idea. And some of the oldest references go back to India, which actually has some of our oldest astronomy in record, period. But if you look back into classical antiquity in the West, you find that almost everybody accepted that there were other worlds, at least all of the various Greek philosophers, particularly the atomists, the people who came up with the idea of the atom and that there was a material reality that was composite. All of these atomists came together to create this doctrine of, which they call it, doctrine of innumerable worlds. And this came out of a belief that the cosmos was infinite and unending. And so, of course, if the cosmos is unending, well, then there's an unending possibility of new things happening and things that resemble our world here. There's an interesting anecdote of one of these philosophers meeting with Alexander the Great, who was this Macedonian warlord, and he told him, this was Anaxarchus, and he said there's an infinite number of worlds out there, and this supposedly led Alexander to weep because he hadn't even conquered one world yet, and he was so depressed about this. How is he going to get to everything? Which is a different way of looking at the world. Okay, so the medieval Muslim writers also talked a lot about this. They interpreted a line of the Quran to indicate that it was said from God that there were multiple worlds, which is quite interesting. That quote from the Quran says, and among his signs in the creation of the heavens and the earth, the living creatures that he has scattered through them. And through literally interprets to upon them. And so this was just a it's hard to explain how much everybody just accepted this as a fact. In fact, people thought all of the planets, all the way up until the 1900s, people really were convinced, and throughout the 1900s, people were really convinced when they looked out, especially as they got the telescope, that they were seeing hints of life on other planets. The most famous example is the surface of Mars. Mars has this really interesting seasonal variation where it appears that these dark patches come and go with its seasons. People thought this was life. There's also if you look at the surface of Mars with like a Galilean telescope, you can see these tracks upon it. And people believed these were canals. They wrote whole books about it. And this was entertained all the way up into the early 1900s. Everybody from Immanuel Kant to Benjamin Franklin championed this cosmic pluralism. And people even thought into the 1900s that the sun and the moon harbored life. The sun has these little black spots on it. They're called sunspots. We'll deal with those later when we get to the sun. But everybody assumed that there was a cold surface underneath the sun where stuff was happening, which is not entirely unreasonable. However, it doesn't seem to be the case. Oh, these are the tracks. I pulled a slide from this. These are some of the drawings from Percival Lowell, who published this book called Mars and Its Canals in 1906. People began doing some spectroscopic analysis of Mars eventually, and this astronomer, William Campbell, was able to show that neither oxygen or water was present on the surface of Mars, in the atmosphere. And that kind of ruled it out. People started to lose their faith in the idea. But all the way up into the 70s, people really, really clung onto this idea that other planets we're gonna find life as soon as we get out there. This is a still image from Carl Sagan's Cosmos, which was produced in the 70s. Which I think I've mentioned before. If you guys haven't checked it out, it's worth watching a few episodes of this. Carl Sagan was like a complete legend. He was like the first modern science celebrity, like way more famous than Neil deGrasse Tyson or something, just like completely adored. And this is Carl's imagination of what the life forms on Jupiter would look like once we got there. And this was not that long ago. Of course, we've found no evidence for anything like that today. But he imagined these little floating jellyfish organisms that were able to sail around and maybe feast on some methane or something. It doesn't turn out to be the case. In fact, the more we go out there and look, the less we find, which is, I think it's a little depressing for everybody too, because as we've gone through, a lot of these searches, into a lot of these quests into the solar system have been filled with the hope that, okay, this next place we go to, we'll see something. But it hasn't paved, it hasn't proved out that way. So what can we look for? Again, if we're going to travel to some of these far reaches that we're about to look at, we're going to look at so we're going to start going outside of the solar system now. If we're ever going to, say we do find one of these really habitable places where life could exist, how do we get there? Well, we're going to have to build a spaceship that essentially has an Earth on it, because it's going to take too long to get there for any one generation to make the journey by itself. And so the process of space exploration is going to be entirely different from, say, the process of exploring the Earth, because you're going to have generations of human beings. Your kids are going to have to be the ones that explore that planet. And you're going to have to bring everything you need with you. I'm not holding my breath for that, but yeah, I mean, there's also, this is where the science fiction and the science get crossed in an interesting way.
Back in Egypt, we wouldn't have thought that we would be able to fly. And now we fly with aliens.
Yeah, I think that's a really optimistic way of looking at it. So there may be shortcuts that we can come up with. As far as we understand physical reality, it doesn't seem to be possible to go faster than the speed of light. And I think a lot of these really wild interpretations of bending reality, as you put it, lack material substance in terms of they're not predicated on a material understanding of why light is speed limited, which is a question I think that people have to really ask themselves before leaping to these conclusions about overcoming that barrier. But yeah, by all means, maintain your optimism that we'll rip holes in the fabric of reality and find our way somewhere else. Yes, like you point out, the Egyptians probably could never have imagined that I would have all of the world's knowledge on a little piece of silicone here in my pocket. Yeah, right on. Right, I don't think it has to be a negative thing, but I do think that, we have to make do with the visions that we have right now, the technology we can imagine. And personally, for me, this is probably the best way that I can imagine getting someplace really far away, which is something like packing up the place into a big moving van and going out, bringing everything you need, and camping along the way, having multiple generations of people. This brings its own set of problems. Obviously, you got to figure out a way to repair the spaceship, and it's not going to be an easy task. So, but this motivates our search. This is kind of why we're doing this. In addition to being just generally curious, science is always motivated by how can we solve problems. This is, if you find yourself in research capacity at some point down the road, maybe some of you will go into some arm of scientific research. You'll always be saying in your grant applications what this is going to do for humans. It's not enough to say, oh, well, it'd just be really cool if we understood how this animal works or something. You always have to say how that's going to translate maybe back to medicine or something like that. And this can be a real thorn, too, because a lot of scientists don't care. They really just want to understand nature. But ultimately, we want to instrumentalize our knowledge. And so, yeah, that's what drives us. We're trying to understand aliens not just for aliens' sake, but we also want to understand where we can go with it. Because, everything dies on Earth periodically. Not everything. Some things make it through, but the Earth is remodeled quite frequently. And we're actually long overdue for another disaster. So it's about time we get that show on the road. Now, astrobiology is a very new discipline. It's really emerged since there was no When I was in college, there was no such thing as astrobiology, at least not in the universities. It's a full-on major at some schools now. I have a cousin who's working on a major for that, teaching over at Duke. And it's becoming a very mainstream practice, but it involves molecular biology, biophysics, biochemistry, astronomy, physical cosmology. I mean, it's just a really cool field that brings in all these different topics, sort of like this class does. So if you're interested in that kind of thing, check it out. You know, going and doing, after you're done with college, if you want to do a graduate degree, it's not a bad idea. It's paid for by the government, which is really nice, so you can get a PhD for free, basically. Actually, you'll get paid to do it, which is pretty cool. And so when I was in college, I didn't really even know about that route. It was pretty much like, if you get a science degree, you become a doctor or something. And so it's really worth considering that you can go and do a whole extra field of deep inquiry in one of these topics if you want. Even if you don't know what you're going to do with it, it's a really cool paid-for basis for whatever you do next. So that's my plug for everybody going out and doing a PhD. It won't necessarily make you a lot of money, but it will set you up with a good basis for what comes next. So astrobiology. There's three basic criteria that we look at. Let's think really wide here. Galaxies, which ones are likely to harbor life? You know, you mentioned the Fermi paradox. If there's life everywhere, why don't we see it? And I want to look at the Fermi paradox through the Drake equation in a moment. But one idea is that our galaxy is just not particularly suitable to life. And so there's a couple of things that we look at in galaxies. The first one's the total mass of the stars in the galaxy. That's going to represent the total number of possible solar systems. And the next thing we want to look at is the amount of metals that those solar systems have, because that's the kind of world that we live on. This is mostly a metal world that we live on, and that gives rise to all these really great magnetic phenomena that protect us and shield us from everything that would be destroying life on this planet otherwise. So we need that special kind of world. So we look for metallicity. And the last thing is the rate of star formation, because really high forming star galaxies are going to pack the stars together. But that's also going to create problems because eventually there's going to be supernovas that mess up those planets as they develop. And so there's this really finely tooled region, but it seems really finely tooled set of conditions that lead to the possibility of life developing. And it seems like galaxies that are a bit larger than ours are actually better. So seems like, let's see here. Galaxies that are about twice as big as us, with about a tenth of the star formation rate as us, can host something like 10,000 times as many Earth-like planets. So we're not necessarily in the best galaxy for that, which might have something to do with why we don't see it. Now the problem is, I was talking about traveling to the nearest star on one of these spaceships, which would take a few lifetimes. Well, not the nearest star, but the nearest, let's say, Earth-like planet. Galaxies are unimaginably large, right? They're thousands of light years across. So there's and then the distance between each galaxy is hundreds of times that even. You know, galaxies are very far away from one another. And so the idea of searching for another galaxy may be out of the question. However, it gives us some idea as to why we don't see more life when we look out there. This is an idea of the region in our own galaxy that might be habitable. There's problems if you go closer to the center, because you're going to run into all sorts of intense gamma rays and X-rays and cosmic rays and supernovas. You might get smashed by more planets. It's just too crowded out there. Whereas if it's out too far, there's not going to be enough material to form the kind of planets that we need, at least to get something like Earth. So we're looking in this little region. The first telescope that even tried to accomplish this wasn't launched until 2009, which is called the Kepler project. And as you can see, the Kepler project, this is our sun, and it's looking in this tiny little cone back through the Orion spur, that's where we're at, and it's looking across this distance of about 3,000 light years. And they found something like 500,000 stars and about 2,500 potential exoplanets. And they have one way of finding these exoplanets, and I think I mentioned it before, but this is kind of a cool picture. The only way you find an exoplanet is you look for that little shadow as something passes in front of the sun. So it's obviously much easier to find planets that are big on stars that aren't too big. So this really narrows the window by which we can find these. Now we've launched a new satellite, which is called TESS, T-E-S-S. It's an acronym. I don't know the words off the top of my head. But so in the 10 years that we had that Kepler satellite going, we found, what I say, 2,500 exoplanets in 10 years. This new one has a different approach. It's actually just looking in a little tiny spherical orbit all around us. And what's interesting is that in just the 4 years, so they launched this one in 2018, in just the 4 years that it's been up there, they've identified already almost 6,000 exoplanets. And so there's probably gazillions of these things everywhere, actually, which is, optimistic, right? This gives us a fair amount of hope, because these are quite nearby us. I think this is only looking in a 200 light year radius, or looks like a diameter. So that's promising, and I think there'll be more and more of these projects being launched. And I actually think that we're going to be seeing quite a few of these bodies. So here is a little map of where we are starting to see these. And of course, within a solar system, they seem to congregate. The bodies that we're interested in are going to be in this very nice little window. And that window has to do with where we can expect to find liquid water. Because water seems to be essential for life. And there's good reason for that, which I'll enumerate in just a moment. So this Goldilocks zone is where we hope to find these. Now, most of these planets are quite chunky compared to the Earth. And that's, of course, because those are the ones that we see the easiest. So you see Earth up there in your top right, I suppose. And some of these other bodies, which are more or less Earth-like, some of them which are thought to have liquid water, actually many of them. And so we'll talk about how they know that in just a moment. There's also this other idea that's been introduced recently, which says, hey, the habitable zone probably doesn't matter as much as we think that it does. Maybe a lot of these planets that are not in the habitable zone also have liquid water. They just have it in a subsurface capacity. And so we're starting to think this about some of the different moons in our own solar system. The idea is that tidal heating, the pull of the different bodies in proximity of these moons, like particularly with Jupiter and Saturn, these huge, massive bodies, that they actually are pulling the inside in such a way that you can get friction, which results in liquid water, heats it. You also have radioactive decay. And so the idea is that maybe a lot of planets that we hadn't thought were in the right place could still do the job. Including these rogue planets, which is another concept that's probably worth throwing out there really quickly. I don't know if we'll have a chance to talk about rogue planets in the future. Just a little animation, but there's been some wild estimates. Anything from, let's see here. One estimate is as low as there's like every fourth star system has a rogue planet, to something like as much as 100,000 times the rogue planets as the stars. So there might be gazillions of these planets that don't have a solar system, that are maybe kicked out of the solar systems as they form, and they end up in this foam in interstellar space. And perhaps these non-orbiting bodies could harbor life, which is a really wild idea. And so if that turns out to be the case, then there's probably way more worlds than we originally thought, which cranks up our optimism level quite a bit. Let's talk about water for a second, though. Water seems to be the main feature that we're interested in when we look for exobiology, when we look for exoplanets that are potentially habitable. It makes sense because we need it on Earth. It doesn't, like I said, necessarily rule out the idea that life has evolved in a completely different fashion on other planets. But water has some very, very amazing and unique properties compared to other molecules. And it really comes down to the fact that water can self-organize, which is a fascinating concept because in a way, this idea of self-organization is what life seems to be doing as well, right? Your bodies rebuild themselves over time. And they do this through automated processes, essentially. Water does it as well. So water has this peculiar aspect where it has both positively charged aspects and it has negatively charged aspects. And this allows it to pair with itself, and under different conditions, it can form structures, right? We know ice is an interesting structure, which is also the result of this, which we call hydrogen bonding, this interaction between the negative portions of the water, the oxygen, and the hydrogens, which are slightly positively charged. But water can form the most bizarre structures under different conditions, particularly when the pressure regimes get very intense, when it's being stretched, when it's being confined. It can form all sorts of really interesting structures. And there's a couple other things that are interesting. So water has this ability to, it can basically interact with positively, as a result of this, it can interact with positively charged molecules. It can interact with negatively charged molecules. You see this with salt, right? Salt breaks apart into its constituent positive and negatively charged atoms, and the water has the ability to surround them very nicely because it has a negative region and a positive region. This is why water dissolves everything. So the fact that water dissolves everything makes it very easy to transport molecules around your body. It's also a bit of a nightmare because it dissolves everything, right? And so things are less stable. And there's some thought that, okay, if life had evolved in a way that on other planets where it used something like a petrochemical to solvate everything, it wouldn't be as reactive. And that might actually lead to more life being created if it was possible that life could have a different basis than water. Water also holds onto itself really nicely. It has this cohesive property, which is part of its self-organization, which allows the water to be dragged up from the root systems in plants. The way that plants work is really, it's really underrated and kind of phenomenal. You might ask, how does the water get all the way up to the top of a 300-foot redwood if there's no heart pumping it up there? And the way that it essentially works is that there are these leaves at the top. The leaves have holes in them, and there's open cavities where the water is able to access the atmosphere. And as the water is evaporated out of the tops of the trees, it pulls. The water is holding onto itself really tightly through these hydrogen bonding, and it pulls the rest of the water as it evaporates right up through the column. I mean, incredible amounts of energy transferred. It's pulling that water all the way from the roots up the column and out into the sky, essentially. And this would not be possible with any other molecule that we can think of. It's just an amazing molecule. It's hard to take it apart from life itself. Water also gives us the pressure. By regulating the salts inside of our cells, we can give this solid character to our cells that has the ability to resist deformation. And then there's this other feature too, which seems to be essential. Every single cell in every single organism on Earth uses this concept of a membrane to isolate the guts of its cells from the external environment. And the entire principle of membranes has to do with the organization of molecules that like the water, the hydrophobic side, versus molecules that don't and exclude the water. And so you make this really nice barrier on all of the cells, all the way from plants to bacteria to human beings. All of our water, or all of our bodies, all of our cells have the ability to regulate the water intake and thereby regulate what comes in and out of our cells. And so, it's just hard to find anything in life that doesn't involve water. It drives the folding of amino acids. Your DNA can only print what the order of those amino acids are in a chain. So they just come out like this big long string. But proteins, like say the ribosome or one of these membrane channels, they all have these really elegant 3D structures. They're very beautiful, complex physical objects. And the way that they get that 3D character is simply by the way that they fold with respect to the water. It's not, you look at these biology textbooks and you see these pictures of the DNA doing that and the proteins doing that. But another equally valid way of looking at it is the water is actually doing all of that, and the little molecules are just going where the water tells them to go, because the water is so highly self-organizing and able to form structures. And there's all sorts of really cool experiments where people are able to see these actual water structures, particularly at close to surfaces. They'll see that the water is organizing into patterns, these layered patterns at the very microscopic surfaces of membranes, like real structures that are potentially capable of doing work. They can pull on each other. There's a whole mechanical structural aspect to the behavior of water, which is, sort of at the frontier of how science is operating. And, I actually did my PhD in water physics, and we found some crazy stuff. I mean, there's processes in nature that people just can't explain with chemistry alone. And I've probably mentioned it already, but we were looking at the bacterial spore, and they can't figure out how these spores stay asleep for millions of years. And spores are amazing because they give us the opportunity for panspermia, right? They can survive in space, they can survive radiation, and they can't figure out how these spores stay asleep and how they wake up. There's no receptor that a particular, we'll know that a nutrient will wake a spore up from a long slumber, maybe millions of years, but we don't find like a receptor that grabs that nutrient in the spore. There's no, typically in your body, the way your neurons work is they'll bind a chemical which will tell the neuron to fire. And most biological processes are canonically described this way with receptor-ligand interaction. You don't see those in bacterial spores, and it's been a wild crisis in biology for the last 100 years. Where's the receptors for these nutrient awakening receptors? Where are they? And we think that the actual structure of water is maybe what's keeping these spores asleep and waking them up, because molecules like nutrients can destabilize water structures. And that can lead to disruption of the whole spore's tensioned body. And once the tension goes, then liquid water can get in and reanimate the different genetic materials and so forth. So I think there's going to be a lot of amazing discoveries about the structures, the silent structures of water in the future. And then, of course, water has this other amazing ability. It can basically buffer solutions. So when you have a really acidic solution, you have some acid that's introduced. We would think of it as being diluted, but it actually can take up that charge. Water can dissociate into, water is typically thought of as HOH, but it can also dissociate and become an OH, or it can become an HHOH. And so it has the ability to stabilize chemical reactions. So yeah, it's hard to overstate the importance of water. And we do see a good deal of it in our own solar system. So this is a pictorial representation of all the water, liquid water on the surface of Earth if you balled it up into a little sphere. And, it doesn't seem to be that much, especially when you compare it to Titan over here, which is the moon of Saturn. Titan, relatively speaking, has more water than us. which is quite fascinating. And it seems like it's quite common. Obviously, the icy giants out there, Uranus and Neptune, they're like 2/3 liquid water, which is wild. So there's a ton of water available. The question is anything living in it? Even the organisms that eat methane on Earth use liquid water as a solvent, so it's not clear we're going to be able to get away from this. Yeah, just a quick survey of the other planets that have it, that we're finding liquid water on. Mars is a good example. There's been a survey in 2018 that has found something like a 20-kilometer horizontal span of stabilized liquid water below the southern polar ice cap. And it's assumed that it's too cold there for liquid water, so there must be some sort of antifreeze structure like magnesium or calcium perchlorate that's allowing the water to remain in a liquid form. In addition to Titan, Europa, which is one of Jupiter's moons, is suspected to have a fair amount of water, which might be allowed to remain liquid due to that tidal flexing that we talked about. Who else? Enceladus, another moon of Saturn, this is a really beautiful one, has these little geysers, actually. And I think this is going to be a really interesting mission. And we've flown through some of these geysers, but we haven't gone down into the cracks. But it's thought that Enceladus out there at Saturn has something like subsurface oceans below this icy layer, and the cracks in the ice allow it to sort of vent and boil out, which is wild. And those vents also contain a lot of other interesting molecules like salts and nitrogen, carbon dioxide, and different hydrocarbons that we could imagine the organisms eating. So I actually think Enceladus is probably one of the biggest hopes for if we're going to find something in our solar system, where we would find it. Ganymede on Jupiter, there's some thought that it also has subsurface ocean. Even Ceres out there in the asteroid belt is thought to have a little bit of water. It's they've found these little plumes of vapor being emitted. It's a tiny little body, and that doesn't totally make sense otherwise. So, yeah, even Pluto, there's some thought that there's a subsurface ocean. So it's abundant in our solar system, which means it's probably abundant everywhere. And unless there's a different way to form life that's easier, it's likely that we'll need to find liquid water. We'll certainly need to find liquid water if we want to go there, obviously, because that's what we're built upon. And so it doesn't seem like it's going to be a problem. There's a lot of liquid water out there. Now, when we go looking for these worlds, we have to depend upon spectroscopy and looking at the atmosphere in order to deduce what might be going on. And we're looking for all sorts of, we can look at the volcanic activity, we can look at the geochemistry, we can look at the surface features, but ultimately, one of our best readouts when we look at the light coming from bodies is going to be the spectra. And, there seems to be quite a bit of signs that there is water out there. We've sent some probes out into the world. There was this Pioneer probe launched, and maybe I'll get to the spectroscopic signatures next time. But I want to finish by talking about I want to be talking a little bit about this Drake equation and why we don't see anybody talking back to us. We sent this little depiction out in 1972, which was quite controversial. The newspapers refused to print this image because it has the naked people on it, which is quite funny. They also removed the female genitals from it because it was too disturbing, which I think will confuse the aliens terribly. But we sent out a message into the world, and it out into the greater solar system, and this is traveling out there right now. It gives the aliens a map to figure out how to get to us. This is the location of our planet with respect to several pulsars that they should be able to back navigate. So, you have to ask yourself if this is a good idea too. Like, do you really want the aliens having a map to your house? I don't know. I tend to be a little bit more skeptical about that, but they did it. And people started thinking, in particular, this gentleman Drake, who was an astronomer, who put together this equation to try to look at all of the factors that would go into what would it take to locate a civilization that was able to talk to us. Why don't we hear anything? And when you put all these factors in, and these are factors ranging from the fraction of planets that might be habitable, fraction of planets on which life might exist, are they able to communicate, all of these different factors. And it seems like even in our galaxy alone, that different calculations of this lead to the probability that there's only one. Some people crank these numbers and they come up with something in the millions, but there's a wide range, and there's reason to believe that the variables that add up to whether we see life or don't, especially the fun, intelligent, communicating kind, might be very infrequent, and it might have to do with how quickly life appears and disappears, like we talked about at the beginning. And so people have started thinking about how we can add in other factors into this equation that might be important, like it's very expensive to spread out into the galaxy. Why do it? Maybe civilizations don't want to. Maybe they only broadcast their message for a very short amount of time. Maybe intelligent life always ends up destroying itself. That's just the nature of intelligent life. So there's all these thoughts about why we don't see the intelligent life that we expect to see, because the Drake equation does say we should probably be seeing a little bit of it. There's also the very real possibility that it doesn't want to be seen, which is really fascinating. Like I said, do we want to be broadcasting a message to everybody, or do we want to sit back and say, how about we don't have a repeat of the conquistadors coming to North America? Because that didn't really work out for half the planet last time. All right, let's pause there, and we'll do the spectroscopic analysis next time. Thank you, guys.